Okay, so today is the 15th seminar we organized with Digiraj and Karen. So today the speaker is my collaborator and good friend Joung, who is at Kyung University in Seoul. He will talk about coadjoint orbit method and how to construct particle actions. Maybe he can tell in more detail some new stuff. Okay, please, Euihun.
Okay, thank you very much. Yeah, it's a great pleasure to give a talk here. Could you actually allow me to share the screen?
Yeah.
Okay, good. So my talk title is From Orbit to Particle. So this is based on some ongoing work with Thomas Basil and my student Tae-Hwan Oh. And actually in this work, we are trying to somehow learn many things, many classical things about the particle actions. And sometimes, I mean, it's all very old story. So many things are understood and many things are known from different angles. However, for us, we find still it's worth to revisit a little bit this old topics. So that's why we decided to write some sort of summary note for us, which we want to finish soon enough, but so far not yet quite ready. So this talk will be another motivation to finish quickly my work. And today, today's talk will be based on mostly on the discussion that I had with Thomas and Tae-Hwan, but also other older works, notably the work with Gomis, Joachim Gomis and Axel Klein-Schmidt and Karapet Christian. There actually I learned many things about this particle action construction using group theory and using group theory data. And also I started to learn many things from classical references. But unfortunately, I'm not quite done with all these reference studies. So let me apologize first if I misses anything, and also some things are very obvious. Actually, yeah, I will not enlist the references, but just I explain what I understood and what I assume that which the content which are relatively less familiar to many physicists. Okay. So why particle actions? So why I decided to study a bit more about this old topics. As far as we, so in the literature, many different approaches to particle actions has been known. So basically, a scalar particle is relatively simple, so probably people are not really bothered with that topic. It's a relatively simple task, while constructing spinning particle action is relatively difficult. So people tried with the various tricks and ideas, and typically we can divide the attempt into probably two categories. How to describe a spinning degrees of freedom, spin degrees of freedom. Either a bosonic way, bosonic variable, by adding some additional bosonic variable, or by adding additional fermionic variables. So depending on that, there are two types of models. And also there are many works which is based on a twistor variable, which naturally describes also spinning degrees of freedom, but somehow relatively exotic space. So space-time is slightly less clear. However, group covariance is much more clear. And also the other method, which is already well known, is the orbit method. And in the literature, So what I learned is that from this with the collaboration with Joachim Gomis, I learned from this nonlinear realization, and also from the other sources it's related to Orwin method. And all these stories, to a certain extent, it's all known. But I wanted to revisit this issue with hopefully some new look. Okay, so yeah, so the one of the reasons to also understand this part collection is that if we understand how to construct a part collection in this way, that means that once we fix a symmetry, we can derive systematically from the symmetry the part collection. Then we can just alter the symmetry part from space-time symmetry to other type of symmetry. And in this way, probably we will get some relatively interesting new physical object. And moreover, actually, another reason that I got interested in this topic is actually the quantized version. If we quantize this part collection, then we will get some oscillators, because part collection is essentially just x and p's. We know that after quantization, x and p becomes operator x and p, which satisfies Heisenberg relations. So we get some oscillator, and we have a Hilbert space. And then, if we understand better this particular action, we can understand better probably what is going on in the quantum side. How a Hilbert space given by oscillator just organized differently according to different symmetry under considerations. Just the same Hilbert space may just organize in completely different looking, depending on which kind of symmetry we want to use to decompose this space. So in the classical side, probably the keyword is that in the quantized oscillator side. Yes.
May I make a comment?
Yeah, sure.
That particle actions are a way also to understand quantum field theory. In fact, there is the word-line approach to quantum field theory. Therefore, that may be another, or maybe related to your point about quantization of particle action oscillator.
Indeed, yeah. After quantization, it immediately gives information about the quantum field theory. Yeah. So, and this decomposition of Hilbert space can be understood either in the genuine quantum side is related to what will be called as what is called as dual pair correspondence, which I will explain a little bit later. And its classical counterpart is a symplectic reduction. So essentially, we have a big phase space, and depending on which symmetry we take, this phase space can be decomposed into different lookings. Different ways. Okay, so before entering into the technical details, so this Orwin method, more or less, the ingredients or the key ideas are like this. So we have so group G, and so in the nonlinear realization side, somehow people learned how to get immediately somehow construct classical particle action using Mohr-Kaplan form. But we may introduce few more steps in between just by going through first coadjoint actions. And since coadjoint action can be described with the Mohr-Kaplan form, and then coadjoint orbit naturally have a phase space structure and symplectic structures. So we can understand how to obtain a classical particle action through this path. But on the other hand, also in mathematics, we understand how to obtain representations out of coadjoint orbit. This is orbit method, and typically these geometric quantizations and this kind of method is used. Otherwise, we can also use more standard path integral quantizations from classical particle action. Then still we will get some quantized theory, and it will naturally explain the representations of G. So this should be all. We should be able to understand all these pieces in a harmonic. Yeah. Yeah. We need to understand all this. So let me begin with the basics. So probably most of the, maybe these concepts are familiar to most of you, but I assume that still some people may not be familiar with the concept. So I took the example of SO3 to explain coadjoint orbit. So coadjoint orbit is essentially like this. So SO3 is the algebra spanned by 3 generators, A1, 2, 3. And the coadjoint space is its dual space with dual generator, tilde 1, 2, 3. Then we can take a vector in this dual space, which is 3-dimensional. This 3-dimensional space is SO star 3. We take one vector, and then if we act group actions on it, then it will form an orbit, which is a sphere actually in this case. So the action is nothing but this coadjoint action. That's why we call this as a coadjoint orbit. And then it's defined in a natural way. And in this way, what we see is that when we fix a vector phi, we can act SO3, but some part of SO3 will leave phi invariant. This group in this case is SO2, and this SO2 is what is called the stabilizer group. And then we can understand that actually the orbit is isomorphic to this homogeneous space, which is in this case a sphere, 2 sphere. And the interesting part of this coadjoint orbit is that it admits a symplectic structure. So the way we see is that on this point, we see that any vector field is can be decomposed into Lie algebra generator. So in this way, we see that any two vector x, y can be associated with the Lie algebra generator x and y, and then we can see. So this we can see that this defines a true form. So more practically, we can we know that this can be obtained using Mohr-Kaptan form, the symplectic two form, and then since Mohr-Kaptan form satisfied Mohr-Kaptan equations, we can see that the potential, symplectic potential for this coadjoint orbit is simply given by these expressions. So in this way, coadjoint orbit, we understand it is even dimensional, and that it admits symplectic structure, so we can use it as a phase space of some mechanical system. So this was a particular example, simplistic example, but more generally, still on coadjoint orbit is isomorphic to the homogeneous space G divided by stabilizer group G phi, and then so because of that, we can see this way. We can take a group element of group G and then decompose into two pieces like this: A times B, where B belongs to the stabilizer part, and the A is nothing but representative of which indicate the orbit points or points in the orbit. Essentially the stabilizer part and then the rest. If we do this decomposition, then and then compute this symplectic potential, which can be actually used as our particle actions. Then what it gives is that we have a piece which is precisely the PDX type symplectic structures, and the rest which depends on the stabilizer part. And stabilizer part is closed, so it's actually irrelevant in in classical physics. However, one important thing is that, so this is boundary term at most of either boundary term or topological term. So if it's exact, it's just boundary. If it's not exact, then it belongs to a cohomology group. So, and it becomes topological. And classically, anyway, this is a number, so it doesn't matter whether we have this or not. But if you consider quantization, actually this is important. And actually from here, what we see is that this gives quantizations of spin. If we consider a spinning particle using this quadrant orbit method, actually spin label S itself, it doesn't need to be quantized at the purely classical level. But if you reason in this way, actually we arrive to the conclusion that the spin should be quantized. So I will come back to this point. So let me apologize also at this level already that so we didn't explore enough the examples of all this in our work. So in this talk, I will be quite sketchy. Yeah, I will try. Yeah, it's a bit pity that I cannot provide many concrete example, but hopefully you can grasp some basic ideas from this. So this however, some simple scalar particle case I can easily take and provide you example, which I learned from actually this nonlinear realization by working with the Joung Gomis and other colleagues. So here, if we take this represented the quadrant orbit point as m times p tilde. P is the dual of translations. Then stabilizer part is r times SO3, where r is nothing but P0, and SO3 is JAB. And then if we decompose the group elements in this way, A and B, P is the stabilizer part and the rest, then what we get is actually symplectic potential is just simply of this type, PA, DYA, and DY. Of course, P is, in order to get exactly P, we need to redefine the parameter V, which is a Lorentz boost parameter, into this way to obtain PA. However, otherwise, it's just this. So in this way, what we get is this. Yeah, we see that we have a nice symplectic structure. So we do have a phase space. However, we don't have any Hamiltonian. So this is just boundary term, which is irrelevant. So there is no dynamics because there is no Hamiltonian. However, if we take a different decomposition, which is used in this nonlinear realization using based on concept of broken symmetry and unbroken symmetry. So then actually essentially what we do is that put these pieces of stabilizer into the other part and make this piece 4-vector, I mean covariant 4-vector like object. So in this way what we obtain is the same kind of object here, but we do have a Hamiltonian part. So we do have a symplectic structure with the Hamiltonian. So here I think I find it interesting, even though that after some consideration, I realized that this is nothing but standard classical mechanics, which we can learn from textbook. But I find it interesting. I find it illuminating. So these tools are obviously related to coordinate transformation because it's the difference comes from how to decompose a group element tree into different way. So different decompositions of group element lead to different coordinate system of group. So anyway, so these tools are simply related to coordinate transformation, or since this piece is same, you can see that this is nothing but a canonical transformation, which actually brings this dynamical system to sort of non-dynamical action angle variable. So that's actually the meaning of this. So here the lesson is that, okay, orbit method can dictate actually both phase space and dynamics. So probably some concept, maybe some people find it a bit weird because if we take all the time these combinations from the orbit, we can always obtain just phase space structures, and then Hamiltonian should be added by hand afterwards. Of course, that's not the wrong. That's a possibility, but we can take another option where we also somehow derive Hamiltonian or dynamics from group itself. That's the other method that requires for that we need to ask something on the coordinate system itself. So if we think this in a coordinate independent way, we never see this aspect of dynamics. So everything is non-dynamic if we reason this in a coordinate independent manner. So somehow this dynamics depends on coordinate system. And then what kind of coordinate system is good to do what we want to do? For instance, describe some particle dynamics. So that depends. So really the coordinate. So it depends on what we want. And in the nonlinear realization side, I mean the choice is made upon what part of symmetry we keep as covariant and what part of symmetry as we keep as broken in the sense not manifestly covariant. So this is the way, but another way of having a manifest covariant descriptions of a system is to introduce some redundant coordinates. So we don't use intrinsic coordinate, but we introduce some additional coordinate, and then which realize the symmetry or the symmetry manifests covariant. So for that, maybe let us, it's useful to consider SO3 again. So if we take SO3, then all the orbits are sphere, essentially sphere, and we know that the sphere, what kind of coordinate we can have? I mean, spherical coordinate or some projective coordinate, stereographic coordinate. But we know that all of them is not manifestly covariant. I mean, it's not easy to act SO3 on Z and phi. We can calculate eventually, but it's not manifest. However, what we know is that we know, okay, sphere is just some hypersurface embedded in 3 dimension. So I know that, okay, this 3-dimensional vector, it rotates covariantly under SO3. So using that concept, using that idea, we can describe this this way. So anyway, yeah. So we can describe using this 3-dimensional vector, 2 set of 3-dimensional vector, Q and P. So in this way, this is nothing but sort of angular momentum. Angular momentum descriptions of this SO3, if you like. However, in this case, we have some problem because we involve the 6 degrees of freedom. Even though that we essentially need only 2 because its orbit itself is 2-dimensional. So we introduced 4 additional coordinates. So in order to get 4-dimensional physical, this is 2-dimensional physical space from 6 dimension, we need to remove 4 degrees of freedom by imposing certain constraint. So in this way, actually, we can reformulate it into a constrained system. So the type of constraint that we will use is like this. So essentially, we have a phase space structures, which we can interpret as ambient phase space in the typical Hamiltonian mechanics. And then we have this constraint here. And then here the constraint is not an arbitrary form, but I assume that the constraint itself is composed into two parts, J and phi. So J itself is actually Lie algebra generator. And then phi is some vector which is related to this representative vector of coadjoint orbit. So in this way, it will we will end up with so this is a slightly more general setup. So using this setup, I will show that how we can obtain, for instance, this sphere out of 6 dimensions, and I will also how we can generalize that kind of construction to other cases. So if I so suppose that you don't have any phi term, then we see that all the j's from a Lie algebra. So this is everything is a first class constraint. This is some well-known example. But in this case, I shifted all this Lie algebra generator by some constant phi. So in this way, actually, what we find is that the constraints will become part of constraint become first class, and part of constraints become second class. So first class constraints is precisely the part of A which corresponds to stabilizer subgroup. So since it's a first class constraint, it removes twice the number of constraints. And then the rest of the these constraints are second class. And then that's precisely the dimensions of the original group algebra minus the dimensions of stabilizer. So in this way, this will remove this much. So altogether, this constraint will remove dimensions of G plus dimensions of G phi. So now if we go back to the SO3 case, what we understand is that actually there are, we should impose three additional constraints if we decide to use these guys. So probably some of you already understand that, okay, this part is SP2, which is, you know, that it is dual in the whole Euler sense, dual to SO3. But in this case, I shift 1 by phi, and in this way, I see that the first piece is a first class constraint, and the other two are second class constraints. And then in this way, altogether, they remove 4 degrees of freedom. So starting from 6, we remove 4, and then we end up with 2, which is describes the sphere. So this way, we can describe covariantly this this kind of system. And then maybe I can add a bit more, which is, so this is, we see that there are constraints with some first class constraint. So there is associated gauge symmetry. So the gauge symmetry is only about the first class constraint, which I call alpha instead of A. Then the symmetry will have this form. So in this way, we can show that, okay, this system is gauge invariant, and the gauge symmetry is only about this first class constraint, which is G phi, which forms G phi. But here, probably another important aspect is that the finite transformation. If we consider finite transformation, actually the action is not invariant, but it shifts by this part, which is nothing but actually the part that I considered here, where B was stabilizer part. And precisely here also H is the stabilizer part, which is the finite the gauge transformation. So in order that this to be gauge invariant, so the effect of this should be 0. There should not be an effect by this term. So, but this is sometimes this is not 0 because it's not exact, and it will contribute as constant. So in order that this does not have any effect, then we have to think the path integral quantization, and in the actions, if it's 2 pi times integer, then in the action it's essentially it's 2 pi I times n, so which is number 1. So it will not affect. So this will lead to precisely this vector phi, quantizations of this vector phi. Actually, the norm of this vector phi. And then this, as I said before, typically in the spinning particle application, this will lead to the quantizations of spin. And then, if you like, we can add more further gauging process here, because we do still have some part of second-class constraints which we may not like. So then what we can do is that we add more field and then make all the constraint as first-class constraint. So this can be done by further gauging, in the sense that I gauge with I introduce additional group element valued field G, and then actually since I add, but effectively it enters with phi. What matters is that stabilizer part does not affect this decouples from these expressions. So essentially what I add in addition is just the dimensions of the orbit, and then everything is first class constraint, so it's all the symmetry is the entire Z, and then we see this precisely the system has the same number of degrees of freedom as the previous one, and then we may take this option. Okay, so this is some setup, some good setup to make the action manifestly covariant. And in doing that, there are at least two methods. The one method is using actually T star G. So this is also quite well understood in the literature, but hopefully just reviewing this in this precisely this context may help maybe to understand this aspect a bit better. I hope so. So in this case, we take T star G as ambient phase space, and then we impose the constraint. So this is T star G, and then we impose constraint as in this case. So then we see that the original all the physical it's like this. The physical degrees of freedom is a 2n minus this, but 2n is nothing but 2 times dimensions of G when the ambient phase space is T star G. So if we compute this way, eventually we see that this is dimensions of orbit. In this way, we see that, okay, we can take this to, if you like, realize orbit action into constrained Hamiltonian system. Another method is that we take this ambient phase space as flat, just like that, and then we realize actually the group, this generator, the constraint as a quadratic, and in this way, what we see is that the constraints is actually formed dually algebra. So we want to describe an orbit of G, but we impose constraints on the dual group G tilde. So this is the method. This method is what is related to this dual pair correspondence, or if you like, symplectic reductions. So this is another method. So these two methods we want to explore more, but so far we didn't explore many examples. We didn't manage to explore the example that we want to cover. But just to comment a bit more, so we see that, okay, this method should be related to the the classical literature about the spinning time model, where we have typical P and X, and the spinning degrees of freedoms are entered into the antisymmetric tensor, which is clearly something to do with the coordinate systems of Lorentz. And second part is either twister or other spinning particle model, this dual pair. So in this way, hopefully, these two methods, this view covers quite considerable amount of the literature which about this particle borderline particle actions. So the first T star G case, just a bit more details about it. So we have this constraint system, and then we have so in this case the constraint is just given by this way, so vector field in Q, group manifold. Q is a coordinate system for G. So this is vector field corresponding to the algebra. It's contracted with this zero variable cotangent vector P. And then so then we have we can take the inverse of this guys, which is actually can be used, which is nothing but the Moore-Cartan form. So this is inverse of J, and this is nothing but Moore-Cartan form. So in this way, if we solve this system immediately, this one, then the solution will be this, and then plugging this solution into this piece, so this is already dropped, then we simply recover this section, which is nothing but quasi-morbid actions. So this is sort of trivial relations. This trivially show how we can reobtain the orbit actions by solving constraints of this system. Otherwise, we do not solve the constraint, but we can proceed another way to treat the actions. So the second method is this dual pair correspondence. So here we have essentially the ambient phase space is some flat 2n dimensional symplectic space, and then there on each we have natural actions of sp2n, and then this sp2n has two subgroups G1, G2, which are commuting each other, so mutual stabilizer. So then there is well-known correspondence between G1 group and G2 or G2 group, which is known as dual pair correspondence or Hall duality. It is basically about the correspondence between G1 representation and G2 representation, but we can view it also from classical perspectives. So before commenting more, I can already mention that actually we can take any. So this is not very restrictive. I mean, we can take any group G1, and then we want to consider an orbit actions of this G1. But if G1, this group is a reductive group, then it can be always embedded in certain sp2n R with a large enough n, and with a suitable G2. So most of the example we may consider can be treated this way. So this is one comment. And then about correspondence, I told you that actually this correspondence between G1 and G2 are actually when we decompose metaplectic representations of sp2n R into G1 times G2, then it decomposes into EREPS G1 and EREPS G2, and then when it appears in a way in one-to-one. But in the classical analog of this is actually when we decompose this ambient phase space, geometric flat space 2n, we slice, we foliate it. Then what we find is that we have G1 orbit and G2 orbit and product of it, and then this orbit should be in one-to-one correspondence. So this is the classical analog of this issue. So and then so we with the method 1 and 2 we want this both methods we want to apply to spinning particle problem, but so far we didn't do that much. But what we managed to do is understand is that it's not actually difficult to identify the orbit corresponding to various different representation or various different quote-unquote particles. So for instance, Poincare case, if we want to add a spin, then so if there is no spin here, then this was a massive scalar. But I can just add this piece S times J tilde 1, 2, then this becomes actually play the role of spin. The reason why I take this is actually precisely I take one element out of a little group of this. So here, in a sense, we can divide this piece, and this is a little group orbit. Yeah, so if we think in this way, it works. But anyway, in the end, so what it works is this. So in massless case, we take just the same massless orbit, massless scalar orbit, but with the additional piece, which is S times J tilde 1, 2. And continuous spin case, this thing should be different. Like if you like, so this is a little group is in this case ISO2. So here among ISO2 generator, this is SO2 part, while here I part is continuous spin case. So this way we will get continuous spin representation. So in this way, if we plug in this orbit data into the method 1 or 2, or just the nonlinear realization, just with the here I got the suitable decomposition of G with this data will lead to spinning particle actions. If we want to do this, then we can either use this T star G method or dual pair method. Poincare is not a reductive group. However, we can view it as contractions of ADS and DS, which is reductive. So it's always possible to use also dual pair. And also here we see that precisely because of these guys, which is, so I will not maybe mention the detail, but anyway, we can see easily this S part is quantized because this is a generator, sort of compact generator. However, this is non-compact or elliptic, so elliptic, or this is non-elliptic. So sigma doesn't need to be quantized, while S should be quantized. So we can also take a similar orbit, determine orbit from ADS or DS. Actually, it's much easier to identify orbit or just classify orbit than classifying representations of or this Poincare group or ADS or DS group. So maybe it is natural because quantization should be something a non-trivial step. So maybe this is natural, but somehow it's in other aspects it's a bit funny. Yeah, also a bit strange that we know that how to describe spiness some fields, quantum field theory, but describing it in a particle as a particle action, I mean, it's known, but it's much more involved. So this is somewhat funny situation. So if we want to use a dual pair to attack this kind of problem, then there is two ways. First is the vector or spinner. So vector is essentially I want to describe ADS, DS as SO 2, D or DS SO 1, D plus 1. And then also take Poincare as contractions of such group. So in this way, all this space-time symmetry can be found as an example of OP, Q, which can be embedded in big symplectic space with a dual group SP2 and R. And then it is well understood that when n equals 1, this describes, so we find the representations here, which is scalar representation. When n equal 2, we have a symmetric spin S. Generically, when n is larger than 3, then it's mixed symmetry. This is already we understand, but deriving the particle analog is probably, yeah, we need to clarify further. And spinor part, because of this isomorphism, various isomorphism, various ADS and GS group in various dimensions can be described this way, which can be realized as dual pair, and one group which can be found as one element of this dual pair group. So, and then this example is actually treated in the literature with quite a lot, with some twistor particle actions, etc., etc. Even though that such an actions, apart from some simple case where constraints are just one-dimensional, many other cases the shape of constraints is different from the proposed type. Because this we see that there is a non-covariant vector phi a. But typically, when people try to put some constraint to realize this kind of mechanical system, they make they don't want to have this kind of non-covariant part. So people typically make a square of this or put some determinant, whatever. So make the constraint much more non-linear. But here, maybe our viewpoint is that even though it looks like a bit non-covariant, but it's only on the constraint side, not in the phase space side. And then all the constraint is quadratic, J is quadratic in the dual pair case, and it's much more easier to treat and also quantize. Okay, so maybe last 10 minutes, I can briefly comment about the generalizations. So far I assume that the group G and the orbit is related to space-time symmetry. But this method itself can be applied to any group G. So we can ask what happens if we take G which is not a space-time symmetry. But even in such cases, the viewpoint that we can take is that always some subgroup of this group G can be viewed as space-time symmetry. Then we can view this group G as some extended symmetry which contains isometry as a subgroup. This is always possible. And in this way, as an example, we can take G as even supersymmetry. And this example will be actually particularly interesting because it will also reproduce or partly reproduce the known example of the spinning particle case. Because if we use supersymmetry, then typically it will describe, if we quantize eventually, supermultiplet, and then if you consider scalar particle case or relatively simple case, in this supermultiplet, generically spinning particle will be a part of it. And in this way, we can describe spinning particle by sufficiently increasing the number of supersymmetry. So this is typical method. Another interesting thing is the higher spin symmetry. However, higher spin symmetry is infinite dimensional symmetry. So it's not that obvious how this method can be applied. Instead, if we can consider rather exotic, but physically rather exotic, but mathematically more familiar color generalizations of isometry. So the example that I want to talk about this color isometry is a three-dimensional one, and we know that in ADS3 the isometry is SO2, 2, which is SO1, 2 plus SO1, 2. And each of these SO1, 2 is isomorphic to SUU 1, 1. So in this way, this helps to dress, if you like, this isometry with some color symmetry, SUN. So essentially, in the end, what we can show is that actually, if you take SUN, N, the generators of SUN, N can be grouped into 3 pieces. The first piece, which is original SU1, 1, and the other piece, which is color symmetry that we decide to add. And the extra generators carries both SU1, 1 and SU index. So this way, SUN, N can be, in certain sense, viewed as color extension, color generalizations of a 3-dimensional isometry. And then we need to, of course, to make a 3-dimensional one pair SUN, N plus SUN, N. In order to get Poincare analog, we need to take inorganic contractions. So we need then, instead of direct sum, and then in this case, again, the construction is the same. We can take an orbit by taking a representative vector, which is, in this case, we can just take the same one because it contains the original isometric part as a subgroup. So there is always an element like this. So then we can write exactly the same way. And here I just will not explain the detail, but in order to, when just reformulate this expression, then at some point we find it useful to introduce some constraints by hand to make the expression more covariant. And in the end, we end up with these expressions. Here, X and P, SUN, N element. And lambda, Lagrange multiplier lambda is just a joint by joint matrix. And we can easily see that when n equal 1, so this is simply reproducing 3-dimensional particle, but matrix descriptions. But what is interesting is that here when we introduce constraint by hand, actually this procedure involves additional orbit than the one we started with. So typically, if you consider the uncolored case, p squared equal m squared. That kind of orbit contains both positive energy and negative energy orbit. So actually, it's not exactly the same as the orbit method actions because it contains 2 orbits. So in this case, instead of 2 orbits, it contains n plus 1 orbit. So when n equals 1, it has 2 orbits, but for generic n, it has much more orbit. And the dimensionality is also very large. In the massless case, probably it's from some certain mathematical viewpoint, it's an interesting example because the orbit is actually closure of a nilpotent orbit. Nilpotent is, if you like, some cone-shaped orbit where the boundary, its closure, the boundary of its closure is another orbit, another nilpotent orbit. That's typical nature of this nilpotent orbit. So this orbit has the same dimensionality. However, it contains many sub-nilpotent orbit of different dimensions, or those dimensions. So I find it as an interesting example of Poisson geometry, because this is a non-symplectic but Poisson geometry. And then we may also ask whether we can quantize, and probably since quantization of Poisson geometry is also interesting topic. So maybe also from that viewpoint, it is interesting. But here, in this case, we already know, in some sense, the answer because we know the representations related to that. That's also from the dual pair correspondence. With some insight from dual pair correspondence, we can see that actually the massive case, the representation can be obtained from the dual pair un, n and un. And the massless case, we replace un by uk, here various k. Of course, the mass parameter is hidden here in this file, representative vector file. Okay, so yeah, because of time, I need to conclude. So in the future, I want to conclude. I mean, explore more examples in the literature, and I need to also learn more. Probably many things I said that was already maybe understood in some corner in some literature. So anyway, I will explore further, and then also cover many examples. And then for the moment, I see that in this way, if we cover many examples using twister or vector or just T star G, we get something which is very close to what is known in the literature, but slightly different in the constraint, in the shape of constraint. As I said, typically people have involved the constraint which is a scalar type, and in this way, constraint is highly nonlinear in the this dynamical variable. But in our case, we always assume that it is just, especially in the dual pair, it's all the time this scalarity. So, and then we can also, another thing that I want to understand is simplex reflection symmetry, which can naturally act on this this phase space, which may lead to the deformation when we quantize. And then I want to understand also this from the classical aspects of this, and also the relation to BF theory, because this coadjoint orbit action can be viewed as a boundary term of the BF action. So then the BF action can be deformed to Poisson sigma model, and then all this direction will be interesting as well. And then also higher spin symmetry, even though it's infinite dimensional, I hope that it can be treated in a similar manner, and probably in this way, maybe we may obtain something one we may call as sigma-like model for higher spins. And then there is also a string extension, which is already explored in to a certain extent in the context of the nonlinear realization, but we can revisit also from this perspective. So. Okay, thank you.
Thank you. Any questions? Kim, it seems that I cannot hear, but it seems that yeah.
Maybe can I ask a question? If I remember properly, the extra in 3 dimensions, the topological term, what is multiplying the topological term is giving the spin.
Yes.
And they are related to the existence of J12.
Yes.
Could you put, okay.
Yes.
When this J tilde is 1, 2?
Yes, 1, 2. It can be any number, but you can take for instance and 1, 2.
But how it goes in, I mean, in 3 dimensions, the point is that the Monet-Cartan form associated to J12, it's a gauge field, it's a U1 gauge field. Therefore, you put that to your action Besso-Minot term. But, and in this case, the coefficient is really giving the spin of the particle, has no dynamical degrees of freedom associated to the spin. And this is for Poincaré or for ADS3. But the point is, when you are not in 3 dimensions, how I should understand this from the point of view of nonlinear realization? Because an element of the unbroken group will transform as non-abelian. And therefore, I don't see how immediately you could add a piece like that, doing the pullback, or I don't know, to the action. Could you comment?
So, yeah, for the moment, I don't have a good. So yeah, so this is still the part that we didn't really work out. So we can, of course, I mean, we can put these things, and then the details is hidden in the decompositions of G. So if we decompose the group element G, for instance, like this. Where is it? Yeah, for instance, like this or the other, probably will not lead to the reasonable expressions. So probably the art will be to put the correct place for exponential I zeta j1 2. It should be somewhere, and then depending on where which place, sometimes we don't get any, we don't see any dynamics for spin degrees of freedom, and then sometimes we get some dynamics just spin degrees of freedom. But I don't, for the moment I don't know.
Okay, thank you.
So that's something that I need to explore a little more, and then also to revisit the same problem with the other method, with the constrained Hamiltonian system.
Yeah.
Okay. Maxim, please unmute yourself and ask.
Yeah, hello. Just some kind of general question. So suppose I have a particle.
Yes.
And I treat it in, suppose, let's avoid some intricacies related to massless particle, suppose massive particle. Then I have a phase space, and phase space, on phase space I have an action of symmetry group, which is Poincare or ADS or whatever we are considering. And then symplectic structure must be also invariant. Is it correct that I can always get this phase space as a symplectic manifold as a result of as a coadjoint orbit? Is there like a general statement that given an invariant mechanical system, you can always you can under some conditions, of course, some sort of reducibility, you can always reconstruct this group theoretical setup? Is it known? I'm a bit ignorant, so probably my question is not really well posed, but I have a feeling that under some natural conditions you can reconstruct all these coadjoint orbits setup.
You mean the reconstructions of the orbit from certain?
Yeah, so it's not a mystery. It's always the case somehow up to some. I have a feeling. I probably am wrong. Definitely, I'm wrong literally. There should be some conditions, but morally, maybe it's not far from
indeed it should be possible.
Correct.
Yeah, from the particle action, I mean, there is phase space, and then we know that there is actions symmetry.
Yeah, but action is if it is Hamiltonian formalism, action is always first order. It is essentially determined just by symplectic structure. There are some tricks with Hamiltonian, but it's not a big deal. And then I can read off, so I have a symplectic homogeneous space of a symmetry group. If it's under some reducibility condition, probably you can show that it arises. I don't know these theorems. Probably it always.
I don't know. Yeah, I don't know. So actually, so this is fairly simple and standard, this constraint system. But so with Thomas, we discussed about this, and then we found also a bit puzzling that I mean, so in many cases we can immediately see the orbit behind the certain constrained Hamiltonian system.
Oh, yeah, that's probably what I.
Yeah, but so what you found puzzling is that indeed it was not clear. I mean, unless we didn't know much about that by reading, for instance, this McKenna's book, or so. Yeah, so indeed the answer I don't know, but probably. Yeah, I don't know.
Okay, thanks.
Yeah.
And another very small question: you mentioned Poisson sigma model in your conclusions.
Yeah.
But it is two-dimensional, right?
Right.
So you mean that you because you're speaking about particles, so it should be something one-dimensional.
Yeah. So
or you want to do Kontsevich-like
boundary term of
multiplication.
BF or Poisson sigma model. So since BF and Poisson sigma models are topological, and then classically, if you treat it, it can be viewed as also boundary term. So BF theory with the boundary. So BF theory, Poisson sigma.
Okay. Thanks.
And then on the boundary.
So it's in the sense of Cattaneo and Felder.
Yeah.
Thanks.
Yeah, so maybe elaborating a little bit on Maxim's question, that was also something related I wanted to ask. So I think actually the question is the first one is very much in order in the following sense. So yeah, so in the construction, on the one hand, you are using the coadjoint action of the Lie group, which is known to yield all possible irreducible representations only for nilpotent Lie groups, whereas for, say, semi-simple Lie groups, the spectrum of the coadjoint orbits is pretty limited. On the other hand, you are also using an invariant bilinear form in your construction, which is known to exist on, well, semi-simple Lie groups and not on the solvable side. So I guess, or of course you know better, but I guess the choice of Lie groups G for which you have a sufficiently large variety of homogeneous spaces you encounter in your construction should be somewhat limited. So you probably won't get all possible homogeneous spaces G by H in your construction, at least in the way of coadjoint orbits, or maybe I'm missing something.
So in this construction, so we don't have any restriction on G in principle here.
Yeah,
So,
but the point is that if you take a Lie group G and then you take the coadjoint action of the group and then look at all possible orbits that you obtain in this action, the variety of possible orbits, it may be very limited. It may not yield all possible homogeneous spaces of that group G by H.
Right. That's
also,
true.
Also that also means that you probably won't cover all possible irreducible representations of that group. So some particles, so to speak, you do miss, right?
Maybe indeed. Yeah.
But this should be symplectic homogeneous spaces. Doesn't it help?
So not all homogeneous spaces admit symplectic form anyway, but if you begin with a classical invariant sort of G invariant symplectic manifold, and you look at all possible orbits, these orbits may be wildly different, and there should not be in general any guarantee that most of those orbits come from a coadjoint action. So I don't think that's going to be true. So for very specific Lie groups that might be true, I'm not sure, but generally I don't see any reason why in this way you might cover all possible irreducible representations of G that might appear in a general G invariant symplectic manifold.
That's true. Yeah, that's true.
But at the same time, if okay, of course, you are totally right. I'm sure I'm just not an expert in this, but nevertheless, in a quantum setup, we know that under some physically meaningful conditions, we do get all representations which we're interested in through quantization of coadjoint orbits, which probably means that in a classical limit, it is also possible to do it somehow.
The coadjoint orbits method was introduced by Kirillov, probably everyone knows that, and it was introduced for nilpotent Lie groups for the sole reason that it is for nilpotent Lie groups that do really cover all irreducible representations by coadjoint orbits. When you go to, say, general solvable Lie groups, then you need some extra constructions over the coadjoint orbit, which goes under the name of Auslander constant, in order to recover all irreducible representations, and that's what we call geometric quantization. And yet, for non-solvable Lie groups, you have a mix-up, so it doesn't work for all Lie groups for sure, but for many classical groups, I'm sure it does.
Yeah, but it seems that it does not misses many.
Yeah, so I'm not saying that it misses any physically relevant one. I'm not the person to refer to for physical relevance, but as a general mathematical construction, I'm just trying to make sure that it is how far it stretches in its generality, that you produce all possible, say, mathematically feasible constructions. Whether or not they are mathematical and are physically relevant, I cannot comment on, unfortunately. Yeah, and I have a couple more questions, if you don't mind.
Yes.
For the construction through the Ho correspondence, the dual pair correspondence.
Yes.
It is true that for a reductive Lie group, you can always find an embedding into a higher dimensional symplectic group where it has Ho dual. At the same time, that embedding is not unique. So you have infinitely many different such embeddings.
Right.
Right. So which one do you choose so that you can interpret it as the physically kind of relevant one? Because different choices will yield you different spectra of representations and so on and so forth.
That is true, yeah.
So how do you choose which one? Or is there any kind of uniqueness?
No, here again, depending on the part collection that we want to obtain. So here, yeah, like in this simple example, if I want a scalar, then just SP2, symmetric spinels, SP4, for instance. So depending on the type of particle that you want to describe, we need to find the suitable.
All right. So in a sense, you should know all possible kind of embeddings and what particles they produce, and then back engineer kind of the interaction you want to receive at the end.
Yeah, in a sense, it's like that. But typically in physics, we know more or less what kind of. So as particle people in physics, people have in mind of certain representation already, and then we have already some data about that representation, which kind of dual pair should be used. So then, so this just we try to find just the classical versions of this dual pair, and then.
Yes, please go ahead. I thought you were
No, just it's about the dual pair side. We have just the group structure itself, but not other part where we want to profit as a classical mechanical system. So just in this case, we want to find such a missing ingredient. That's it.
So in any case, it is up to the physicist kind of to try and find the kind of Hoe embedding which yields the necessary spectrum, right?
Right.
I see. And a similar question regarding the kind of the TG star kind of approach. So you take a homogeneous space, so to speak, an orbit, and then you are saying I can realize this homogeneous space kind of quotient map as let's call it Hamiltonian reduction due to constraints. So given such a homogeneous space, I can introduce corresponding constraints so that the constraint phase space is exactly the base manifold, and it satisfies this and that desirable properties. And then the question is again, how unique is your choice of the constraints? And if there are several possible such constraints which yield the same vibration, how do you choose which one is the more relevant one?
Again, here is the same answer. So if we want to, so the procedure should be like that. So we want to describe certain particle, which we know as a representation of certain space-time symmetry, say G. And then we know that, okay, so this representation should correspond to this orbit of a group G. Then okay, with this data, okay, I'm okay. So I have some given orbit and given G. Then I will write down some particle actions. So the method will be then generically three, either just this nonlinear realization method, just Morakatan form, and then choose suitable decompositions of G, and then blah blah blah. And just
right.
try to find the most convenient or other two methods, T star G.
What if someone comes and says, well, I have another set of constraints which does the same job, right? It reduces the phase space T star G to what you have to do, what you need to do at the end, the quotient kind of phase space, but it's completely different. So can you somehow prove that yours is the more physically motivated one?
We're saying that
because I don't know, maybe there is kind of uniqueness for that phase space reduction with constraints. I don't know. If there isn't, then how do you choose one?
here you are saying that so the constraint which is not given this form, like the vector field given by Lie algebra generators, but the other constraint which lead to the same orbit.
Yeah.
Yeah, I don't know. I don't know. But let me see whether I can. That's a good idea.
Yes, just a purely theoretical kind of considerations and may not be relevant from any practical point of view. Just curious.
Yeah, but that's probably that will be something that I should understand that, because in these constructions, either here, the dual pair we don't have necessarily all the linear in P, but T star G all the time linear in P. Dual pair it's not always. And then we know from the classical mechanical system, many well-known gauge systems, if you do the Hamiltonian analysis, then constraint is not necessarily linear in P, and indeed it can be more. So in the whole duality case, we can describe the same representation with a different variable. I mean, so we can take different, take P and Q or A and A dagger or different rotations. So depending on that, the shape upon looking of the this generator differs. Indeed, and then the way to describe the same representation, but the description of the representation is completely different. For instance, sometimes vacuum and then excite everything with a dagger, and sometimes it's just some realized space of function on some manifold like that. But it's exactly the same, but depending on which variable we take.
Right. So there
So
might be
here also, I don't know.
a theorem that relates kind of. There might be a theorem you can prove that, say, any two sufficiently reasonable, say, set of constraints that results in the same reduced phase space are related by a canonical transformation or so. I don't know. Or maybe not. That would be maybe interesting.
Yeah,
or not. I don't know.
It's canonical related by canonical transformation. Another related, maybe possible related thing is again the constraint used in the other literature. So here, so we have, it's all the time, how to say, covariant constraint.
Right.
But people like to put the invariant constraint. So like J square or that kind of object as constraint. So it's tricky to show the equivalence. Also in that case, very naively, yes, okay, this looks like, and then the proposal is made by that, more or less, based on that. Okay, these constraints, I mean, it should be invariant quantity. M is invariant quantity, so I want to relate M to certain number, S to certain generator. So in this way, they make it some invariant. But again, there it's very tricky. And then also, typically they do in the literature. I mean, some Hamiltonian analysis are done, but very messy, and sometimes it's a good guess, and sometimes partly.
So if we restrict to, say, manifestly covariant constraints like yours, at least in the class of such covariant constraints, is there any kind of uniqueness, or is it still a hard question?
I don't know. Yeah, in the case of dual pair, probably putting some bilinearity and then that kind of thing, maybe imposing such constraint will trivialize the problem and it should be unique. But otherwise, relaxing more the input. No, I don't have a good idea.
That's fine. That may be a very technically relevant question. Okay, maybe a last very minor question. I think I saw somewhere on your slides a tensor product of Lie algebras being considered as a Lie algebra. What does that mean?
Yeah, that's maybe legal expressions here.
Yeah, how do I interpret this as a Lie algebra on its own?
Yeah, it's so the generator. So this generator say X A. This guy is generator Ti. Okay. But there is another generator which looks like XA Ti product.
Yeah, how
can be
do I
viewed in this way.
interpret this as a Lie algebra?
Yes, or if you like, just put some index I here, maybe more safe, more easy to buy.
Yeah, I'm trying
So-
to see how.
So
how...
just maybe take it this way. This is just some extra generator, which is adjoint here with respect to SU1, 1, and also adjoint with respect to SUN by adjoint.
Yeah, but
Okay.
then this is a tensor product of the two adjoint operators, isn't it?
Tensor product.
Or
of
is it
two-
the direct sum of the two operators? I'm trying to understand. So once you write them in a tensor kind of notation, I guess this is a tensor product of two representations.
Yes.
But for Lie algebras, we normally well, the tensor product of two representations doesn't become a Lie algebra, right?
Actually, the hidden construction behind this is that we make use the fact that actually SU and N can be easily uplifted to U1, 1, and then this guy is UN, N, and then the Lie algebra U11, and then U11, U11, and UN can be again uplifted to the associative algebra with the usual product rule. Then we compose directly this way.
Yeah,
as an
absolutely.
associative.
So as an associative algebra, I can take it 100%.
Yeah.
But
And then eventually
as a Lie algebra,
and then eventually take the commutator part. Then
does it,
such
does it
algebra is a
close?
certain Lie algebra which happens to coincide SU and comma.
So what would be the Lie bracket of two such elements x, a, I, say x tilde?
So this is
J.
XA, TI, TJ. So that will be this 1/2 XA. Of course, as a Lie algebra, this does not make sense. But if there is a backup associative algebra, which gives meaning to this anti-bracket, anti-commutator, sorry, then it can be okay.
Yeah, does this become a Lie bracket? So does this close as a finite dimensional Lie bracket? Because I understand that SU and N on the left hand side, if you take the universal enveloping kind of algebra as an associative one, and then you take the right hand side in the same way, then this may give the same associative algebras, isomorphic. But on the level of Lie algebras, I'm having difficulties realizing the third direct factor as a Lie algebra purely.
So if you like, this construction is like this: U1, 1 and UN. So I take the fundamental representations of U1, 1, UN. So this is matrix. And then matrix as associative algebra. And then take a direct product. And I make some direct product associative algebra first.
Right.
And then I take commutator Lie algebra of that guy.
Which may happen to encompass the full associative Lie algebra, right? Because when you take an arbitrary matrix associative algebra, there is no guarantee that the purely kind of commutator Lie algebra part doesn't encompass all of it, right?
So in this case, if I remember correctly, only the identity part, diagonal part.
So as commutators, you don't get higher powers of x and t, or you do?
No.
No? That's interesting.
Because yeah, no, in this case it's so that's probably peculiarity of U type.
It might be, yeah, because from the
Yeah,
general
peculiarity of U11 and UN. Okay. So if we take, for instance, any Lie algebra G1 and G2, and then take certain representation G1, and then with that matrix, if I take associative, then it will become much larger.
Yeah, that's what I mean. Yeah.
Yeah, but in this case, U type guys are just this center guy.
That's interesting.
Yeah.
And also looking at the formula you wrote in red in the top right corner, you see the commutators of T, they produce elements linear in T again, but the anti-commutators, they are quadratic in X.
Right. So with the matrix description, we can show that it is still with some structural constant plus identity piece in most.
Yeah, that's very specific. Yeah.
Yeah, very specific. Yeah.
Okay, thank you very much for your patience.
You're welcome.
Any other questions? I have one question about the SO3 algebra example you wrote before. So I'm just a naive question about this, when adding this phi term, so the commutators don't change at all here. I mean the constraint algebra.
So if we do take the commutator, these two, we get these guys, right?
Yeah.
But this is equal to phi. So C2, C3 commutator becomes essentially phi, which is constant. So that's why this is second class.
And the rest of the commutators, I see, C1, C2 gives C3.
Yes.
No,
this commutator doesn't affect.
Yeah.
C1, C3 commutator, this doesn't affect. But these two commutator, which becomes C1, but now C1 is not really the QP part, but there's another piece.
Yeah, I was somehow wondering, but probably, yeah, that was wrong. That this could be somehow interpreted as deformed oscillator, but probably not. Right here, it somehow reminds the deformed oscillator has similar construction where you have just one number that modifies your commutator in some way, but here it doesn't.
Probably not. Yeah. Probably not.
And you mentioned that there's the hot duality, so this SO3 is some kind of hot dual to what the.
In this case, SP2R.
The same. Okay, the same SP2 that is responsible for the phase space in a sense.
Phase space was SP6R. The 6-dimensional phase space.
That's the extended one, but the real there is one particle degree of freedom, right? So
yeah, but that is a different SP2R.
Okay.
That's different. That is different. That's not as. Anyway, so that's a sphere part. So it's different. Yeah. So here is just a typical is SO-SP duality, dual pair correspondence. Is where we have a compact SO set.
So SP6 together with SO3 are embedded in some SP18 or something.
Sorry?
So the hot duality is realized in some SP18 where you have SO3 dual to SP6, something like that.
No, in this example, is SP6 is the embedding.
So
and then the dual pair is SO3 and SP2R.
So what is the physical space? Somehow you have physically just one degree.
SO3, the sphere S2. Yeah. So what is not explained in this case is, well, not explained, but not commented is the phase space which is compact. So if the phase space is compact, then when we describe it as particle, actually it's weird because so naively phase space dimensions, like a sphere is 2 dimensions, and it's a 2-dimensional particle naively. But actually, if say the phase space is some non-compact part times sphere S2, then what the natural interpretations as particle is that the sphere part is just spin degrees of freedom. Yeah, we need to decompose spherical harmonics, and then we have to decompose. So the compact part of phase space should be treated completely differently when we think about particle. Even though it's a phase space, but we need to rather do the decomposition like that.
And another naive question. So you mentioned about this coordinate dependence of the description. So there was one description where there was no dynamics, and so one can somehow think of it as going to rest frame, or is there any physical interpretation in that sense?
I don't know whether it can be interpreted as a rest frame or that kind of way, but typically, I mean, it is related to this action angle variable. It's essentially the same idea. Essentially here, constraints, you see that there is Hamiltonian, which is 1, if you like. Hamiltonian becomes constant, and then this is nothing but this action over action angle variable.
But you cannot do the same for massless particle, right? Or can you?
Massless particle, I think you can do that, do the same thing. I don't know, but I think
you can, then the interpretation of rest frame wouldn't make sense.
I think it should be possible. Yeah, I didn't do, but I think it should be possible.
Okay, maybe we can stop recording if there are no more questions.
So